family visit recently, and my mother is here for all of you who are interested and wondering, wow, you raised that guy? So my mother asked to come to a county commission meeting. She's like, you have some, like a real boring meeting. I was like, yeah, come up for oil and gas. It's going to be real boring. So my mom is here. She's a truck driver for about 30 years, hardworking blue-collar lady, and I'm just hoping that she kind of stays quiet during this. And I love her very much. Mom, you can just raise your hand and say hello. I just want to make sure the deputies know where she's sitting.
I'll be quiet.
Okay, thank you. All right. Thank you, Mr. Chairman.
So the first item, item 5, is going to be a consent agenda item. Item 6 is going to be a discussion about the early funding of the library bonds with some public comment. Then we're going to have 4 presentations on oil and gas, followed by we're going to be accepting 1 representative from each governorship. I'm probably saying that wrong. Representative from each title or federal governor. And then we're going to have comments and questions and discussion by the commissioners. So although governor comments, we're not going to limit to 3 minutes. We would appreciate brevity so that we can get out of here before 1 o'clock. And I hope you've all got your bedrolls. And with that, could I have a motion to approve the agenda?
So moved. Second.
Madam Clerk.
Commissioner Blunt?
Aye.
Commissioner Linrose?
Aye.
Commissioner Chapman?
Yes.
Vice Chair Eichel?
Yes.
Chair Hyde?
Yes. Consent agenda. Anybody want to bring the minutes off the consent agenda? Have a motion?
So moved. Second.
Madam Clerk.
Commissioner Blunt?
Aye.
Commissioner Linrose?
Aye.
Commissioner Chapman?
Yes.
Vice Chair Eichel?
Yes.
Chair Hyde?
Yes.
Thank you, Councilor. Gentlemen, carry on.
Chair, Commissioners, workload on this was divided. I was involved
with the assessment of oil and gas potential. My colleague, Dr. Reinhardt, was involved with the assessment of risk, although some of our data, he utilized some of the data I produced to assess risk and susceptibility. After the last meeting, let's see, where do we go here?
Sorry, we can't hear you.
You can probably just use the page down on the keyboard.
Okay, there we go.
The page down.
Page down, that page down, okay? So to talk a little bit about oil and gas potential, there were some questions after the last meeting and after our presentation on the last meeting, and it was inquired why we had not utilized some of the data that Thrust Energy had to assess oil and gas potential. We attempted to obtain data, seismic reflection lines from Thrust Energy to do the supplemental report and to update our assessment of oil and gas potential. But Thrust Energy, because of the proprietary nature of the data, which they had purchased from a third party, was not able to supply us with that information. We came up with an alternative way to basically obtain a proxy for that data, which was from some published gravity studies. And then we also ended up using a thermal gradient model, thermal maturation model that was produced with existing data, which we were able to combine with the gravity data to obtain a proxy for the seismic data. It is not as precise as the seismic data, but I do believe it gives us a reasonable assessment of the oil and gas potential, which was better and more detailed than what had been presented the last time. If we look at the basin as a whole, we concentrated the supplemental work on just the Albuquerque Basin part of the county. And that's divided into several different parts. There is a transition or a divide between the San Juan Basin and the Albuquerque Basin on the west or the left of this slide. There is the Ziana uplift that comes down north-south through the center. That shows up very well on the gravity study. That Ziana uplift has been drilled by one deep well, Shell Oil Company number 1 Santa Fe Pacific well, which was drilled in the early 1970s. To the west of that is the Calabasas subbasin of the Albuquerque Basin. That's a low area between the divide and the Ziana uplift. Unfortunately, no wells have been drilled down into the deepest part of that. And with the gravity data, we were able to get some information as to how deep that actually went, which allowed us to better assess the oil and gas potential of that area. To the east of the Ziana uplift, you have the Santo Domingo subbasin to the north, and then there is another divide or a high area that separates the Santo Domingo subbasin from the Calabasas subbasin. And those four elements, the Ziana uplift, the Calabasas subbasin, the divide, and the Santo Domingo subbasin, all have distinct different oil and gas potentials based upon basically depth to the sediments of interest. Again, this is the cross section we presented the last time. Regional cross section, which goes from northwest to southeast. It's a vertical slice through the rock. It's based on extensive analysis of well logs, and one can see the different strata in there rising and finally being truncated at the surface of the ground by erosion. And then over to the east, you can see the major faults found in the Albuquerque Basin, and you can see the strata dip downdropped along those faults. Okay. The major productive units, or the productive units from the Manco Shale within the Albuquerque Basin, are shown in green and blue, the Manco C zone and the lower Manco Shale. The Manco C zone is by far the primary productive unit within the Albuquerque Basin. And if we look at the Sandoval County part of the basin, all lower Mancos wells are also completed in the Manco C, and they're vertical wells. The Manco C provides almost all the production and is the only Mancos unit that provides where the wells are completed solely in the Mancos, in the Manco zone. All the horizontal drilling that has taken place in the San Juan Basin have taken place in the Manco C. That, we believe, because of this, is the primary objective, with a secondary objective being the lower Mancos Shale. And you can see the down drop in here. They are several thousand feet lower when you get into the Albuquerque Basin. If we just take one summary and look at the upper Manco Shale productive wells, and the area is shown in blue up there in the northwestern part of the county, is where we see production of oil and associated gas from the Manco C zone. The Albuquerque Basin is shown to the south with very, very few wells drilled in. What I've shown now is essentially the result of our thermal modeling, the thermal model we developed. And what it shows on the right is a vertical slice of what happens when you go from essentially no burial at no time in the upper part of the block down to increasing depth, therefore increasing temperature and increasing burial time in the right. So it essentially shows the history of what a stratum that bears that is a source rock for oil or gas goes through. And when it's only buried very shallowly, you only get biogenic methane. When you start to bury it more deeply, at first you start to generate just a little bit of oil along with some gas. And then finally, as you mature it more or bury it more deeply, you subject it to greater temperatures for longer periods of time. You essentially come to the area of maximum generation, what we call peak oil generation, which is in what is termed the lower part of the oil window. If you bury that even more deeply, you end up naturally refining or cracking the oil that's been generated into gas, first a wet gas, which is propane, butane, and ethane, and then finally into a dry gas, which is only methane. And so that's all that's left at that point. The block that's shown on the left, in the lower left, is a highly magnified microscopic image of a shale that is a source rock, and you can see the mineral matter, which is the light brown and the white. The organic matter, which was deposited with the mineral matter when the shale was deposited, is shown in the darker brown, and then that big, huge yellow thing in the middle is a collapsed spore. Okay, when that matter becomes buried more deeply, subjected to higher temperatures for a greater period of time, it is converted, part of it is converted into natural gas and oil. So that's where the natural gas and oil comes from. What you see on to the left of the block in there showing the generation of oil is you'll see three scales in there where we have used various parameters we measure on the rock that determines where in the oil generation stage the rock is. Basically, it determines us the thermal history of that rock. Okay. We don't have this for all of the wells in the basin. We don't have the hard data for all of the wells in the basin. So what we did is we developed a thermal model based on the wells where we had the data. And we would end up with a vitrinite reflectance estimated or predicted from basically the depth and the thermal regime that the well is in. Where we have no wells at all, we were able to use the gravity data to estimate the depth to the top of the primary potential pay interval, which is the Manco C, and from that predict where the maturity might be today. For reference, let's look at a well where we have analysis of samples, rock samples from the well, and that's the Getty number 20E Jicarilla B well, which is way up where we get maximum production in the county from the Manco C. And this is an example, this is an analysis of shale samples obtained from the well, and we have analysis, good analysis of what we call the vitrinite reflectance measurements. We can see at that point, you can see the purple window in there, the Manco C in that area has reached the stage of peak oil generation, and that is why we get significant oil production out of the Manco C up there. That has generated oil, and it is right now, today, within peak oil production, and so that has generated that. Let's look at the Shell number 1 Santa Fe Pacific well, which was an exploratory well drilled in the early 1970s. We have samples from that well, and from those samples, several different parameters of thermal maturation have been measured. And for the Manco C in there, this was drilled on this Ziana uplift, which is a shallow area, sort of in the middle of the Sandoval County part of the Albuquerque Basin. And if we look at the vitrinite reflectance measurements, the thermal alteration index, and something we call Rockeval Tmax, they all point to the fact that this Manco C in that interval is right at the top of the oil window and has only just begun to start generating oil. Okay, when you're in a shale unit, and to get oil out of shales, and this is seen by a survey of published studies of numerous shale units, okay, generally maximum production is obtained where you get peak oil generation, which is in the stippled window. You can get some lesser amounts of production where you're anywhere within the lower oil window above that. But as you can see, when you're on the Ziana uplift in there, we're not even close to the oil maturation in there. Which explains why, when the Shell drilled that well, they saw no signs of oil within that well. Okay, it just isn't there because it wasn't mature enough. Let's go now to the Shell number 3 Santa Fe Pacific well, which was drilled also in the 1970s. Okay, that's on the west edge of the Calabasas subbasin and is on an uplifted fault block on the west edge. It's still fairly shallow, but deeper than in the first well we looked at. And not surprisingly, our predicted value of vitrinite reflectance, about 0.8. It has not yet reached the stage of peak oil generation. It is possible to get, there is some potential indicated, but not maximum potential in this area. It just hasn't been buried quite deeply enough to attain maximum potential. It's still there. You might still get something out of the rock. Okay, our indications are from the data we have from the Shell number 3 Santa Fe Pacific well was that they did not have any indications of oil when they drilled the well. One of the difficulties of assessing that data is in the early 1970s, absolutely nobody was looking for oil from shales. They were looking at it from other conventional reservoirs, which they did not find. Now we'll look between the two. And that is along kind of the middle of the Calabasas subbasin. And this is directly between the first 2 wells we looked at. Okay, the gravity data indicates that the Manco C in here is buried more deeply than either to the east on the Ziana uplift or to the west in the Shell number 3 Santa Fe Pacific well. In this area, we're getting to the point where we're essentially our predicted vitrinite reflectance indicates maturity is right at the top of peak oil generation. So there is definite potential for oil and gas within this area. It has been buried more deeply. What we don't have, and so because of this, we've assigned the potential for this part of the Calabasas subbasin as moderate. We don't assign it as high because we do not have a well that has basically shown us documented encounters with either live oil shows, or a flow of hydrocarbons from the Manco Shale out of the Albuquerque Basin. So if we were to have an actual documentation of live oil out of the Manco C in the Albuquerque Basin, then that would be a high potential to be assigned. But until a well is drilled to actually test that, we don't know. If we move to the south and we go into Bernalillo County, where the Albuquerque Basin gets much deeper, and the Manco C is down at depths of 20,000 feet or greater, that's 4 miles. Things are much warmer down there. It has been heated up much more. In that area, our predicted vitrinite reflectance would be down within the gas window, and any oil that had been generated would have been converted or naturally refined into natural gas. that might have some attraction in a time when gas prices were much higher than they are today. So the potential in there, again, is moderate for gas. It's essentially very low for oil because any oil in there has been naturally converted into natural gas. So we don't see oil potential down there. Okay, we also looked at this for some other areas in the basin, used the same methodology. We can come up with essentially a map that shows axial areas of oil and gas potential within southeastern Sandoval County in the Albuquerque Basin part of the county. We see an area of moderate oil potential along the axis of the Calabasas subbasin. To the east on the Ziana uplift, where you're thermally immature, low oil potential. To the west on the divide between the San Juan and the Albuquerque basins, you're thermally mature, and we partly know this by studies of maturation in the Albuquerque basin, which we presented last time. Okay, the areas in between, it's a transitional or a gradational boundary. There is no hard set boundary between where you have low potential and moderate potential. It's gradational. So you end up being, so your best potential is within the axis of the Calabasas subbasin. When you go to the south, into Bernalillo County, things are much deeper. You have moderate gas potential because the oil has been converted into natural gas. And then if you look at the structure and the gravity data, it shows the deepest part of the basin going up south, essentially under about where Corrales is. Again, you would find you're in the natural gas zone. There is another oil window when you go into the divide between the Calabasas and the Santo Domingo subbasin. Okay, that is high enough. In that area, we estimate, we don't have any wells drilled, but from the gravity data, we can estimate that the Manco Sea is down at a depth of 10 to 11,000 feet. Our thermal model would indicate that it is in the zone of peak oil generation, so you would have oil potential in there. When you go further to the north into the Santo Domingo subbasin, you get much deeper and you go back into the gas zone. So the potential up there is for natural gas. Sandia Mountains, low oil potential, partly because you have no Manco Sea. It's all been eroded from the uplifted mountains. Same way with the Sierra Nacimiento. Hagen and Bayment has a low oil potential. There was a study published in a New Mexico Geological Society guidebook, I believe it was in 1999, by Dr. Bruce Black, an eminent petroleum geologist, who was the prospector who generated and had several wells drilled in the Hagen and Bayment. His conclusion was that oil was generated, it had been trapped in the Hagen and Bayment, but due to subsequent erosion had leaked out naturally by natural causes. And so therefore the Hagen and Bayment has a low oil potential. Okay. That's the end of my presentation. I will now turn it over to Dr. Reinhardt to talk about susceptibilities and risks.
I have the keyboard.
Yes, Nate.
All right, thank you, Ron. So we went through and basically updated and clarified a lot of the criteria that I use to assess susceptibilities and risks for groundwater contamination during unconventional oil and gas operations. I'll tell you right now that there were not very many changes to the initial assessment. We refined it a little bit, and I'll be highlighting the major transitions, or major changes. to sort of refresh everyone, when we talk about susceptibility, we were talking about the proclivity for a hazard to happen. This is sort of a toy example. This is, if we think about susceptibility of falling objects in a colleague of mine's office, along his west wall, he has high shelves, things sort of way up high, nothing secured. If there was an earthquake or some other sort of shaking event, it is very likely to have falling objects. Along the east wall, he doesn't have anything up high. Now, so that means along the east wall, it has a low susceptibility. Now, in terms of risk, what is risk? Risk is a balance of the proclivity of a hazard occurring and of the costs of that hazard occurring. Those costs can be monetary, they can be in terms of health. So if we think about risk in his office from falling objects, he doesn't spend any time over along the west wall because there's no desk. He doesn't really do very much over there. It has a relatively low risk. Now, along the east wall on the right, where he spends a lot of time, if there was something that caused objects to fall, it would have a moderate risk. Okay, so this is to illustrate the difference between susceptibility, which is the proclivity for a hazard, likelihood of a hazard to occur, and risk, which balances both the proclivity and the consequences of that hazard occurring. Okay, so if we think about unconventional, and when I say unconventional, I mean horizontal completions followed by hydraulic fracturing. If we think about groundwater contamination risks, I'm not talking about any of, or hazards, I'm not talking about any of the other associated environmental hazards associated with unconventional operations or general oil and gas operations. There are two pathways. One is up from the reservoir into the aquifer, and then one is from the surface, from a spill, down into the aquifer. And so we consider these susceptibilities separately. So here, as you can see, there's a few different ways for oil and gas operations to affect the aquifer. So the one that most people have heard about is during hydraulic fracturing operations. There is the possibility of upward leakage, where the fractures either go through the seal above or encounter an open fracture, an open fault, and then push fluid upwards into the aquifer. Okay. Another pathway is also during the hydraulic fracturing operations to intersect with an existing oil and gas well that penetrates the unit, which may have either an open, it may be under production, or it may have a leaking seal. And then you can also, in that case, have fluid migrate upwards. In terms of the most likely pathways, and I'll talk a little bit more about why I'm saying most likely pathways for leakage from the Manco Sea, the most likely ones are in the vertical portion of the well, where if the well bore leaks and there are multiple layers of steel and concrete between where the oil and gas is and where the aquifer is, if that leaks, you can end up with groundwater contamination up there. It sort of flows out through the leak, as illustrated by the inset figure, into the aquifer. Now, that is probably the most likely pathway. So, in terms of changes to susceptibility that we made, let me just quickly go through the major susceptibility factors. So, first of all, the greater the distance between the reservoir and the aquifer, the lower the susceptibility. If there are a number of different sealing formations between the reservoir, in this case the Manco Sea, and the aquifer, the lower the susceptibility. If there is a lot of existing older oil and gas wells completed in the same formation, that also will increase the susceptibility. And then lastly, there's the permeability of faults and fractures. So if there's sort of highly permeable faults or highly permeable fractures, that will increase the susceptibility. There is also a general just likelihood of accidents happening in the vertical portion of the well. And from sort of broad-ranging studies across the United States, from Pennsylvania to the Denver-Yalsburg Basin in Colorado and the Eagle Ford in Texas, there's between 1 and 5% of wells leak in the vertical portion. And that's primarily seen in terms of what is called stray gas, which is methane, that exits the well and then is found outside. Now, one of the refinements that we made, or that I made, is that we are including in the susceptibility, not just in the risk assessment, but in the susceptibility assessment, the water well density. So after reviewing again the literature, there is some evidence that shows that if you have a water well that's pumping, it ends up concentrating the stray gas into it. And that is a function of distance from the vertical portion of the oil and gas well. And then, because it is a major risk factor, we re-examined the reservoir pressure in the Albuquerque Basin to ensure that it was actually what is called normally pressured. So if you have a normally pressured reservoir, that means that under normal conditions and even after fracturing, there isn't a driving pressure to push oil and gas up. This is a source of uncertainty in our study, as well as we assume that faults and fractures in the Manco Sea at depth where oil and gas is generated seal. And that's based off of a pretty wide literature. Okay, so those are the major changes to susceptibility. I want to emphasize that if there are concerns regarding groundwater contamination due to unconventional oil and gas operations, it is vital to go out and monitor your water quality before oil and gas operations begin. There are cases, and this has been documented, of stray gas being formed by bacteria in the aquifers, and that sort of complicates identifying whether or not a contaminant is naturally occurring in the aquifer or coming from an oil and gas reservoir. So it is very important before oil and gas operations begin to go out and get water quality data. Okay. So one of the other things that we were asked to do was to refine our or quantify how we switch between thresholds a little bit more clearly. So now we have a table that lays this out. One of the major changes is in terms of the vertical thickness. After reviewing the same papers that I had reviewed before, I increased the vertical thickness required between the Manco Sea and the formations above. So this is the thickness of shale that is above the Manco Sea, immediately above the Manco Sea, that essentially did not change any of the susceptibility levels because there is so much shale above the Manco Sea. Excuse me. And so essentially that change went from sort of less than 1% probability of a fracture, propagating further to that is the maximum thickness that a hydraulic fracture has been documented to go. Another addition is that we refined the horizontal distance to faults. This is based both off of an existing study that was incorporated in the first study, as well as a more recent study that I found. And so this is also should be the horizontal distance to existing or abandoned oil and gas wells. This is essentially how far a fracture can go sort of out from the well, to the best of our knowledge. There is uncertainty with that, as with all of these metrics. And then in terms of, and this gets a little bit, when I made this table, I kind of flipped things around. So the next one, which should be highlighted, is the horizontal distance from the vertical portion of the oil and gas well to an existing, in this case, domestic water well. And so it has a low susceptibility at greater than a mile, between a kilometer and a mile, a moderate susceptibility, and within a kilometer, a high susceptibility. So as I said, about 1% of the oil and gas wells that we know have been drilled in the last 10 or 15 years using modern methods, leak. And if you're within a kilometer, then there is a reasonable probability that the stray gas from the oil and gas well will appear in your water well. And then in terms of other susceptibility thresholds, conductive faults or fractures, no current evidence of deep connection, has a low susceptibility. Current evidence of deep connection has a high susceptibility. In terms of reservoir pressures, if it's less than hydrostatic or equal to hydrostatic, which is sort of the weight of water that's on top of the reservoir, that means that you won't get upward leakage sort of spontaneously, then you have a low susceptibility. And then we also, using existing literature, parsed out a couple other different levels, which we didn't actually need to use in this study. And then, similar to the previous original report, number of sealing formations above 1,900 feet above the reservoir. So you have sort of the initial safety seal above the reservoir, and then if you have additional shale above that, that's sort of additional safeguard, and then every sealing formation above that. In both the San Juan Basin and, as far as we know, in the Albuquerque Basin, we have multiple sealing layers. And so in all cases where there is oil and gas potential, there is more than one sealing layer. And if that's the case, then you have a low susceptibility because, due to that. And then there's the municipal water well distance. And so if you're more than a mile away, because this serves so many people, which is more of a risk thing, but also because this generates such a large cone of depression because of the capacity of the pump. If you're more than a mile away, you have a low susceptibility. If you're less than a mile away, you have a high susceptibility. This is based off of the same set of papers that I use for the general water well guidelines above. Okay. The other pathway, which is more visible and actually more difficult to quantify, is downward transport. Can I actually get a bottle of water from someone? I'm getting a little dried out. Thank you. All right, so in terms of downward transport susceptibility, this is what happens if there's a spill at the surface. So there are 3 different ways, and I clarified 2 of the ways because in the original report they were sort of lumped together, that this can get into the groundwater. One is if there's enough spill and it's close to the surface water, it can run off directly into surface water, and as folks know, here in New Mexico, if it gets into your stream, it will get into your groundwater. The other way is for it to directly infiltrate downwards and go into the groundwater. Okay, so this requires sort of a large volume and a sustained spill, right? So this isn't sort of a short squirt on the surface. This is sort of a very large volume of contaminant that sits at the surface and has time to infiltrate. The other way is if you infiltrate and it doesn't reach the groundwater table, the water table can rise and fall. All right, so every season and between years, water tables go up and down and up and down. And so there's a possibility, and this was encountered in Albuquerque recently, where the water table came up, hit a contaminant plume, spread the plume out, made the situation worse. And so that is the third way. I'm calling that entrainment, groundwater entrainment of the contaminant plume. So essentially, the levels that I chose for susceptibility have remained constant for this surface. I went through and quantified exactly why I set those thresholds. And then I explained the susceptibility levels for entrainment. Now, one thing that I want to emphasize is that to understand how far a contaminant will penetrate the unsaturated zone where there isn't groundwater, but there is some residual water left in the sediment, that's a very complicated analysis. And so I use relatively simple methods to do that. And those are documented in the report. And I used a couple of different ways of doing that. And so I'll talk about that a little bit more here. So in terms of groundwater entrainment, for another study that I've been doing for about 4 years, I've looked at tens of thousands of hydrographs from around the state, including in the Albuquerque Basin, in order to assess regional groundwater storage change. And as part of that analysis, I observe sort of normal, annual, and decadal changes in water levels. And across the state, usually water levels are going down, but where they are coming up, they usually come up at most 30 feet. Okay, especially in the Rio Grande basins. If you're in a fractured bedrock system, say in the Sacramento Mountains, you can end up with larger oscillations. But in the Albuquerque Basin, San Juan Basin, there are relatively low oscillations, at least not more than 30 feet in terms of upward migration. And so we set the threshold for groundwater entrainment at 50 feet between low and medium, and then above 100 feet is a low susceptibility. Okay? And then in terms of depth to water to protect from surface infiltration, so this is a case where you have a spill, and the question is how far will it go? Okay, so I did this calculation two different ways. So the first way is assuming a constantly ponded long-term spill without a volume specified or a surface area on the surface specified for the spill, and mapped out how long it would take for the contaminant to get into the groundwater, or how long it would take for it to go certain depths. So using parameters for a sandy loam, which is a common texture and sort of particle size distribution in Sandoval County and throughout New Mexico, it takes about 30 days for it to penetrate 50 feet. And it takes about 60 days for it to penetrate about 100 feet. Now, if you have a sandy sediment, your intuition will tell you, so loamy sand is sort of, there's a bunch of clay-sized stuff in there and silt as well as sand in it, sort of this mix. If you just have a clean sand, it's all sand grains, you'll move water through it more quickly, or contaminant through it more quickly. And so that means that areas that have, say, like an arroyo or a stream bed that have coarse grain size, contamination can infiltrate through those very, very quickly.
How much longer do you think you will be?
I'm almost done. All right, so then, and then essentially the susceptibility level for the arroyo bottom remains the same. If you're in an arroyo or in the floodplain, the susceptibility is high. And just real quick, in terms of the infiltration, the other way that we did this, or I did this, was I assumed that there was a spill of 20,000 gallons, which is the maximum spill in the EPA report from 2016. There are some higher volumes that have been reported later. So I assumed 20,000 gallons, which is 0.06 acre feet for folks who are farming. So it's a very large spill. I assumed it was spilled over a 10-foot by 30-foot area, infiltrated vertically, and then at some point the plume will stop migrating down because there are capillary forces or surface tension forces, the same forces that cause your water to rise on the side of your glass, that will cause the contaminant to be retained in the soil. Okay, and so if you go down to that sort of retention percentage, volume percentage, it will penetrate about 50 feet, and then it should stop. And so that was another reason that we set the infiltration depth at 50 feet for moderate and 100 feet to be safe to low susceptibility. Now, from susceptibility, we move to risk. We don't double count in terms of sort of well density on this. If there's no oil and gas or low oil and gas potential, then there's low risk. If you have more than one water well per section, you increase the risk one level from the susceptibility. If you have new wells within 1 mile of oil and gas development, this is the case for parts of the region west of Rio Rancho, and then you have a high risk. If there's a dependence on groundwater supply for drinking water, you increase the risk one level from susceptibility. That is the case for the vast majority of Sandoval County. And this is local around wells. If you have presence of streams, rivers, and other surface water, that's a high risk. In other cases, you use the susceptibility level. So let's look at maps. All right. So I'm going to focus in on the susceptibility. I'm going to focus in on the Albuquerque Basin. So you can see that region that Ron told you was the Calabasas Basin, that still has a medium susceptibility like we discussed last time. Surface water susceptibility is low. There is a miscoloration on the figure. Surface water susceptibility in Rio Rancho is low. Aquifer susceptibility is high. Down in the floodplain, and I want to emphasize this, the aquifer and the surface water susceptibility there is high. And this is one of the places where there is oil and gas potential that Ron saw in his study. We also revised some of the susceptibility levels around the Sierra Nacimientos and the southern Jemez Mountains, where there are faults that have evidence of deep flow from CO2. There is no oil and gas susceptibility, or not susceptibility, oil and gas potential there, but the susceptibilities, if there was development, would be high around those faults. In all cases, if you're near a domestic water supply or a municipal water supply within a mile, then your susceptibility increases. If you're in an arroyo, your susceptibility is high. In terms of risk, so this is actually a change in the Calabasas Basin, and this is because of the planning documents that Mike Springfield shared with me that are publicly available on the web. I just didn't see them during the first round. The aquifer susceptibility, because of the dependence on groundwater moving into the future and because of the planned development in terms of municipal water wells in the Calabasas subbasin west of Rio Rancho, the risk is medium to high. The surface for aquifer contamination for surface water is still low. The depth of water in this region is hundreds of feet. Within Rio Rancho, the aquifer risk is high, susceptibility is low. In the floodplain, in the valley, the aquifer and surface water risks are high. Areas that don't have oil and gas potential have low risks. And throughout the San Juan Basin, except in arroyos near homesteads and towns and municipal wells, the risks have been assessed as low. Okay, so that's a lot of information. This is what we offered to give to the commission. This is what is in the, I think it's 40 some odd page supplemental report. Overall, there were a few changes. We included water well distance from exploration wells and the susceptibility. We more carefully considered overpressures or possible overpressures. We increased the vertical separation distance that had no effect on the susceptibility or on the risk because of the thickness of the Mancos Shale. And then, we want to emphasize that there is additional information needed on the horizontal distance to conduct faults or fractures. So throughout the study, we assumed that faults and fractures in the San Juan Basin and in the Albuquerque Basin, and this is based off of multiple literature, multiple papers where, folks are worried about sealing of shales. There is, however, some uncertainty about, how conductive those faults and fractures are at depth. And then, we had more detailed explanation of susceptibility and risk levels, and formalized, particularly for the downward contamination pathway, we formalized the analysis for susceptibility. And with that concludes our presentation.
Thank you. Any quick questions? Good. We'll move on to the working group presentation.
All right, thank you.